Okay, and then this one is for the converging diverging nozzle, because you want to reach the supersonic, so you attach a diverging part. So if you see at this part, you can see it's the same with the one that we see previously, right? When you have P equal to P exit, P inlet equal to P exit, there is no flow, there is no pressure change, right? And then when you reduce the pressure exit, you can see that the pressure starts to decrease. Why it increase again? Of course, coming back to Bernoulli equation, right? When you have the area decreasing, the velocity increasing, velocity increase, pressure decrease. Then in the diverging part, your area is increasing. When your area is increasing, the velocity decrease. When velocity decrease, pressure increase. Okay? This is the case because you haven't reached the critical condition. When you have reached the critical condition but you cannot maintain it, okay, it will behave like your subsonic flow. When the area increase, the velocity will decrease, and then the pressure will increase. Okay? If you push it further, you decrease the pressure further, then you will have a supersonic region. This is the supersonic region. Okay? This is where you have a supersonic flow in your diverging section. Right? So if you can look at it, see that the pressure over here is lower than the critical pressure. You can see in the subsonic region, the pressure will always be lower than the critical pressure. Okay, so you can only reach sonic when your pressure is equal to the critical pressure, and you can only reach the supersonic when your pressure is lower than critical pressure. Okay, if you cannot reach that, then there is no way you can reach a supersonic flow. Okay, and in this supersonic region, right, if something happened there, right, there is some instability in the flow, you will have the so-called normal shock. What happens when you have a normal shock? The pressure will suddenly increase. When the pressure is suddenly increased, you know that your velocity will suddenly decrease. Right? And it's even worse because you are already in a diverging area. When your pressure increases, right, your velocity will decrease rapidly. That's why at the end of the normal shock, you will have a subsonic flow. Okay? So before the shock wave, you will have a supersonic flow. But right after the normal shock, you will have a subsonic flow because there is sudden increase in pressure. So if you look at if you look at this thing, this is your if you look at P1, it will be like this, then increase rapidly, right? Whereas for the velocity, it will go there, and then it will decrease rapidly. Okay. How about the density? The density will be constant, sure? Sure? Increase. Why increase? Because pressure is increasing. Right? Density is P. Sorry. Yeah, P over R. Okay, so when you have that, that's what will happen. Okay, and okay. This normal shock, when you have this normal shock, your isotropic condition is no more valid. Okay, this is non-isotropic. So P naught over there will not be the same with P naught over there. Okay, you will realize later on that the only thing that maintain is the T naught. T naught over here will be equal to T naught over there. Why? Because of the conservation of energy. Right? Because there is no heat input, no work input, so whatever there has to be there. So only T naught constant, but P naught will be different. Okay. Now, if you have done this problem example, okay, I have to apology to you because this semester I cannot go through the problem example as what I did previously. 12 week, my boys and my girls. We have no time to do that. But hopefully, because this one is step by step, right? So you can see here I demonstrate to you that if you do the calculation using the equation and you compare it with the table, you get exactly the same result. Right? So you can see that at the throat when the Mach number is equal to 1, T star over T naught is 0.8333. If you look at here, it's exactly the same, 0.8333. Okay? But okay, if I may suggest you, you try what happens if you have Mach number 1.1. Okay, you try. If you have Mach number 1.1, you do the interpolation. You want to do interpolation, right? You compare the interpolation with the result and see how far it goes. Right? How different it is between those two. Right? You compare 1.1 here and over there and see what will happen. Of course, you cannot use this one. This one is only for Mach number equal to 1. Use the next one. Right? When the Mach number is not equal to 1. Then you compare. Okay? And yeah, you can use this one. You can compare this with that. It will show you that this one gives you exactly the same result. Okay? But if you try using 1.9, you will see there will be some different. Okay? Okay? So don't tell me why don't we use the table. Of course, if you can use the table, you are pleased to do so. I mean, you are free to do so. It's up to you, right? That is your test paper. It's up to you what you want to do with that test paper. Okay? And it's up to me how to mark that paper. Both of us has our own freedom. Okay, so that's about it. And now, interesting story is if you compare the mass flow rate. Okay, this one is the mass flow rate at the throat, and this one is the mass flow rate at the exit. You can see that both is the same, right? Because the conservation of mass tell you that no mass can be created nor destroyed, so you cannot have a different result. Doesn't matter what, whether you have isentropic, you have is non-isentropic, has to be the same. Unless you have a storage there, right? If you have a storage, then the flow is non-steady, right? Because there will be some storage. If you have a single flow steady, then rho AV has to be same. Okay? Okay, this is a shock wave. We have gone through it very briefly last time, if you remember. I think you forget it. Ipavali has wiped out your memory. Okay, so you can see this is the normal shock wave, and this one the oblique shock wave, right? This one is more complicated. Okay, I suggest you to learn about it if you want to work with Lockheed Martin or with Boeing or with some Virgin Atlantic, Virgin Galaxy, whatever that you dealing with this oblique shock, then you have to learn about it. Okay, as I highlight during the previous class, it is not there in our lecture note. Okay, this is for you to enrich yourself. Okay, but hopefully with the information that given to you, you have enough background to learn about this. Okay, If you want to discuss with me, yeah, you can do that. Okay, but that one will not be in your test or your final exam. Only for hardcore fluid mechanics. Okay, so we will just learn about the normal shock. Even the normal shock, if you look at the equation that we have, right? Okay, this is some simple story about it. Mass flow rate has to conserve because you have a conservation of mass. Energy is conserved. That's why you get T naught is equal to T naught 2. T naught 1 is equal to T naught 2 because H naught 1 or stagnation enthalpy before the shock wave and right after the shock wave is the same. Okay, and the area of point 1 and point 2 has to be the same because this one is just a thin layer. If you can say it's just a thin as this, so the area has to be constant because this is condition just before and this is right after. Okay, the area, it happened at the same area. That's why you got this story. Okay, the only difference now is your entropy. Previously you have isentropy condition or isentropy condition where your S2 minus S1 is equal to 0, but this one no more. There will be some increase in the entropy. So how do you calculate that? Okay, so the increase in the entropy is given by that. Right? That is how you calculate the entropy. So S2 minus S1 is Cp, natural logarithmic of T2 over T1 and T2 over T1. Okay, so if I give you a question, what is the increase in the entropy, you're supposed to know how to calculate it, right? Because you have this one, and you can calculate your P2 from P1, and you can calculate your P1 from P0. You can calculate your P0 from the initial or the inlet condition. Okay, if you come to the tutorial, you know that you can calculate P0 and T0 from the inlet condition. When you get the inlet condition, you can calculate the stagnation properties. If you can calculate the stagnation properties, you can calculate the properties just before the shock wave. Okay. If you know the condition just before the shock wave, you can calculate the condition after the shock wave. Clear? Okay. If you know the condition after the shock wave, pressure and temperature, of course you can calculate the enthalpy changes. Right? So you can calculate the enthalpy. So basically that's about the compressible flow. Right? Any questions?